We are gonna start soonish. So just first of all, welcome to the last day of the conference, and I would like just to remind that we will go for 50 to 55 minutes for the talks, okay, and plus questions. Let's try to stick to the timetable. So our first speaker is Laurent Desvillettes, which is a pleasure for me to introduce, and he's going to give us a talk about some new results on the Landau Fermi Dirac equation. Please, Laurent.
Okay, thanks a lot, Jose. So thanks for the invitation. Let me first say that already my first slide has a typo because my university, which was Université de Paris up to the 1st of January, has not the right anymore to use this this denomination. So it's a university of something, and we'll see in the coming months what it will become. Anyway, so it looks like I can't. Yeah, okay. So let me first say a few words about the vocabulary that I will use in the sequel. For a given equation, I will call, as usual, either Lyapunov functional or entropy, any function h which is real valued and which decreases along the flow of the equation. So it is entropy in the mathematical sense, minus entropy in the physical sense. I will call H usually this entropy, and I will call D the entropy dissipation, which is defined as minus dH over dt along the flow of the equation. And I will also say that the entropy structure is strict when we are in a situation in which there is a unique function that I will call usually f infinity, which is such that this function is the only equilibrium of the equation. So A is the only function f which satisfies A of f is equal to 0. And it is also the only function which satisfies D of f is equal to 0, where D is the entropy dissipation. And finally, it is the only function which minimizes the entropy itself. That is the only function such that h of f is equal to h of this function. So when we are in this situation, I will speak of strict entropy structure. And what we expect, of course, in this situation is that when you let t go to infinity and you consider a solution of the equation that you're looking at, then it converges to this equilibrium, this unique equilibrium f infinity. This is, let's say, the simplest case of the Lassalle's principle, and it's something that can be proven for ODEs, and for PDEs it can be proven provided that you have a nice compactness structure in the equation. Anyway, I will mainly look at equations, kinetic equations with which are related to collisions, either in a gas or in a plasma. And so I first introduce the Boltzmann collision operator with the usual formulas. And with the vocabulary that I used in the previous slide, we know that a strict entropy structure is given exactly by Boltzmann's H theorem, which was proven more than 150 years ago now. And to be a little more precise, this happens, for example, when B is strictly positive almost everywhere, where B is a cross-section of the operator. And in the sequel, I will denote by Hc of f, the quantity integral of f log f, which is the entropy for the Boltzmann equation. And the C here means that it is a classical entropy, the entropy which corresponds to cases in which we have a non-quantum situation. I will also look at the Landau collision operator, which can be obtained by the grazing collision limit from the Boltzmann equation that is written in the previous slide. So this one is maybe a little less classical than the Boltzmann operator, but it was already discussed in the workshop by Jessica, for example. And so I will present it very briefly. Let me say that this is a second order operator in the sense that you have a divergence in front and a gradient of f which appears inside. And let me also say that you have in its definition the presence of this capital pi of v minus w, which is a notation for the projector onto v minus w orthogonal. So if you prefer, it is identity minus v minus w divided by its modulus tensor product with the same. And this projector naturally appears when you do this grazing collision limit in the Boltzmann operator. So since this operator can be obtained from the Boltzmann operator, it is quite natural that it inherits its entropy structure. And as we shall see in the sequel, actually it inherits even the strict entropy structure, which is not completely obvious if you just want to use the grazing collision asymptotics. And this is, of course, this holds with the same classical entropy integral of f log f. Here is some more vocabulary. This is a zoology of the Landau collision operator. So this classification that I present is completely coherent with the one that Renjun presented yesterday for the Boltzmann operator. The gamma, which are strictly positive, are called hard potentials. Gamma equal to 0 is corresponds to Maxwell molecules, and gamma less than 0 corresponds to soft potentials. But one has to be a little careful when one uses this in the Landau operator, because this gamma corresponds to the power that you have in the function psi when you put in front of the projection operator v minus w to the square times psi, and not psi itself. So it is coherent with the Boltzmann equation when you have this extra factor v minus w to the square in front of the projection operator. Okay. Let me also add that specifically in the case of the Landau operator, it is quite useful from the mathematical point of view to sort of distinguish between the so-called moderately soft potentials and the very soft potentials. And the limit is that gamma is equal to -2. And this is an important mathematical limit, which is basically the limit for which above it, it's possible to have a good, very good theory of spatially homogeneous solutions of the Landau equation, and under it, then the solutions are, I mean, smooth solutions are not known to exist in general. And let me finish this presentation by saying that the most important case, and maybe the only important case, is the one when gamma is equal to -3, which corresponds to the Coulomb interaction. It was already identified by Landau in, I think, 1938. And it is also the case which is obtained when you do the weak coupling limit starting from a system of particles. Okay, so this is for the presentation of the standard Landau equation. Now that I have presented the equation, I would like to say a few words about the entropy dissipation, which is related to this equation. So this quantity can be obtained in two ways. The first one consists just in taking the time derivative of the classical entropy along the flow of the Landau equation, and then you just compute and you get what is on the slide. And the other possibility is to start from the Boltzmann entropy dissipation, which is given by Boltzmann's H theorem, and then to perform the grazing collision limit, and then you end up with the same quantity, which is written on the slide. The way it is written usually is the one which is on the first line, in which you have still the cross-section, which is psi times this v minus w to the square, multiplied by f of v and f of w. All of this is integrated over v and w, and you have inside this projector, which is acting as a quadratic form on the vector gradient f over f minus gradient f over f taken at two different points, v and w. So this is a standard formulation for the entropy dissipation. However, after many years working on the equation, it seems to me that there is in fact a presentation which is more efficient when you want to do computations, which is the one which is on the last line of the slide, and in which you replace the projector acting as a quadratic form by the norm of the cross product between v minus w and the vector gradient f over f taken at two different points. As you can see, there are at least one reason to use it, is that it uses only one line instead of two on the slide. But actually, there is a little more. One of the points is that the v minus w to the square, which was appearing in the first line, is now absorbed inside this, this norm. And you end up with the psi in front of f of v times f of w. And this psi is really coherent with the cross-section of the Boltzmann equation. Okay. So let me now try to use this formula in order to present the entropy structure for a slightly more complicated model that I want to introduce now, and which is directly related to the title of the talk, which is what is sometimes called the Landau Fermi Dirac operator. So this consists in taking the Landau operator and introducing by force the Pauli exclusion principle terms, 1 minus epsilon times f, where epsilon is a quantum parameter. And in order for it to make sense, you have to introduce them where in the operator you have f. So instead of f, you will have f times 1 minus epsilon f, and you will keep the gradients as they are. So you still have gradient f of v and gradient f of w in the operator without any change. So you just change the f in f times 1 minus epsilon f, and you do not change the gradients. So in fact, this operator can be obtained by taking the grazing collision limit when you start from a quantum Boltzmann operator, which are, I mean, those are sometimes called Boltzmann-Nordheim or Welling-Uhlenbeck. Here, I will use the terminology Boltzmann Fermi Dirac because I want to insist on the fact that we are considering only the case of fermions in which one expects a Fermi Dirac statistics at the end. So when you do that, you have to remember that this operator makes sense only for functions which are between 0 and 1 over epsilon. So this is a consequence of the exclusion principle of Pauli. And also you have to keep in mind that in real physics, once you sort of non-dimensionalize the quantum effects, the parameter epsilon is usually extremely small. And for cases in which you're considering electrons, you expect typically epsilon to be of the size of the order of magnitude 10 to the minus 10. Okay, so those quantum effects for many applications are very small. Okay, so it's quite natural in the mathematical treatment to call the parameter epsilon and to try to see what happens when epsilon goes to 0. Okay, so of course, formally, what you can immediately see is that you recover the classical Landau operator when you let epsilon go to 0 in the Landau Fermi Dirac operator. Now, what is the entropy structure of this Landau Fermi Dirac operator? This is slightly less well known than the entropy structure for the classical models. So let me spend a few minutes trying to explain. So the first point is that you have to change the definition of the entropy itself. So instead of considering the classical entropy integral of F log F, you have to introduce this more complicated quantum entropy, which I will call the HFD, like Fermi Dirac. And as you can see, F log F is replaced by two terms. The first one is epsilon F log of epsilon F, and you have to put 1 over epsilon as a factor in front. And the other one is the integral of 1 minus epsilon F log of 1 minus epsilon F. The first thing you can see is that if you let epsilon go to 0, then the second part goes to 0 because it becomes 1 log 1. And the first part goes to integral of F log of epsilon F, which is almost the classical entropy. Actually, you have the term log epsilon times integral of F, which remains. But when you are in a situation in which mass is conserved, so that the integral of F is a constant, you see that this is a classical entropy up to a constant, which still depends on epsilon. So whenever you will take derivatives of the entropy, it's really like you have a perturbation of order epsilon of the classical entropy. So that is the first thing, and this has been known for a very long time, probably as long as the definition of the quantum collision operators. So probably in the 20s of the 20th century. And what has also been well known for a long time, but certainly much less, is the form of the entropy dissipation for the Landau Fermi Dirac equation. So here, once again, you can obtain this term by just taking the derivative in time of the Fermi Dirac entropy along the solutions of the Landau Fermi Dirac equation, or you can obtain it by taking the grazing collision limit in the Boltzmann-Nordheim equation for Fermi Dirac case. And I think it's important to try to see the differences with the usual Landau entropy dissipation. So there are basically two differences. The first one is that instead of having the product f of v times f of w inside the integral, you now have those extra terms 1 minus epsilon f of v and 1 minus epsilon f of w, which come directly from the Pauli exclusion principle. But those terms now also appear in the terms with the gradient. So if you remember, you have this projection operator which acts like a quadratic form. And in the standard Landau equation, you have gradient f over f at point v minus gradient f over f at point w. And now you have to put inside also this 1 minus epsilon f terms in the denominator of those quantities. And as we shall see, once again, it's a very good idea to replace this projection operator acting as a quadratic form by a cross product. So this is just a different way of writing things, but it turns out that it's much more efficient in the computations to have the last line of the slide for the entropy dissipation associated to Landau Fermi Dirac. That is the integral of psi times f at point v, f at point w, the Pauli exclusion term, and then the norm of the cross product between v minus w and the gradients which are inside the norm. Of course, it's not as classical as for the Landau equation to try to write down the H theorem for this model, and I would like to present to you what I think is the shortest proof of the case of equality in the H theorem for this model, which will, since epsilon can be taken as a 0, which will of course be also a proof of the H theorem for the Landau equation itself. So this amounts to try to see when this entropy dissipation is equal to 0. since you have an integral of something which is positive inside, which means what the term inside has to be equal to 0, let's say almost everywhere, if you take f, which is not smooth enough. And you can see immediately that there is one possibility, which is that f is equal to 0, and this already appears in the standard classical kinetic equations. But you also have the possibility that 1 minus epsilon f is equal to 0, which means f equal to 1 over epsilon. So if you want to go further in the proof, you have to eliminate those two cases. And so you consider functions f which are not equal to 0 or to 1 over epsilon. And then you see that the quantity inside the norm has to be equal to 0. So to summarize, if now I compute the solutions of the Landau Fermi Dirac entropy dissipation equal to 0, that is, I'm trying to do the H theorem, the equality part of the H theorem for the Landau Fermi Dirac case, then I start from V minus W cross product with the gradients, which are inside the big parentheses in the middle of the slide, is equal to 0. And in order to perform the computation, I have to suppose that f is different from 0 and epsilon to the minus 1, or the terms inside the parentheses are not well defined. And also, I will restrict the computation to the normalized case, in which I will suppose that the mass, momentum, and energy of f are respectively 1, 0, and 3/2. And finally, I can impose that the directional temperatures, which are defined as the integral of f vi vj, up to a rotation, are a matrix which is diagonal. So I will suppose that integral of f vi vj is equal to 0 if I is different from j. This does not lead to a loss of generality. Okay. Okay. So now I think this may be the computation of the talk, which I think is central. So I will spend a few minutes really trying to detail it. So you start from this cross product is equal to 0, and as you can see, it has a nice symmetry in V and W. But after many years of working with that kind of quantities, what I discovered is that the first thing you have to do is to break the symmetry and to expand the term. So you expand it, and you end up with 4 terms, one in which you have only V, one in which you have only W, and 2 terms in which you have both V and W appearing. And you start from there. So I've written it again at in the upper part of the slide. And now it happens that the shortest way to the result consists in choosing the right multiplier, which is in fact Wi times f of W, where I is one of the components of W, and Wi is one of the components of W. And you multiply this quantity by what is equal to 0 in the upper part of the slide, and you integrate along W. And actually, that is what gives the results the most quickly. Let me say at this point that the traditional proof, which goes back, in fact, to Boltzmann himself, would consist in taking derivatives of the quantity, which depends on V and W up there. So here, instead of taking derivatives, we basically integrate against the right quantity. Okay. Let me show very briefly how it works. So since you multiply by something which depends only on W and you integrate, you see that the first term completely disappears because integral of Wi f of W dW is equal to 0, because we supposed that the momentum of f is equal to 0. Okay, so the term in V completely disappears. Then you have the second term, which is W cross product with something which depends on V. So in this one, in the cross product, you have basically 2 terms, okay? So Wi djf minus Wj dif, let's say, One of them disappears because you have supposed that integral of wi wj f is equal to 0, because you have taken the right rotation in order to have this. And so you end up, so this second term just gives you the integral of minus wi square f w dw times one component of gradient f divided by f 1 over 1 minus epsilon f. So this is what appears in the first line of the secant equality. And then the terms which are in the second line on the slide, once you do this integration in W, they just give you something which is an affine function of V. Okay, it was already an affine function of V when it was not integrated. When you integrate, it remains an affine function of V. And so you end up with the fact that the directional temperature in the component I, which is integral of wi square f of w dw times this derivative term of f in V is equal to something which is affine in V. And doing an integration by parts in the terms which appear in the computation, you end up with what is on the last line. Let me write that again on the upper part of the next slide. So for all I different from j, you end up with the equality that a quantity which depends on I times something which is a derivative of the with respect to j is equal to something which is an affine function of V. So since the only thing which depends on I is this directional temperature, actually, since you are in dimension 3, you can, let's say, pick 1j, and then you see that integral of wi square f of w dw is the same for the two i's which are not equal to j. Okay, so for example, if j is 1, then you see that the directional temperature are the same for the components 2 and 3. But you can take for j whatever component. So this ensures that in fact, all the directional temperatures are equal. And since the sum of them is equal to 3, it is 2 times the energy, you end up with the fact that all directional temperatures are equal to 1. Once you know that, you can replace the equation in the upper part of the slide by the one which is in the middle of the slide and which tells you that djf divided by f times 1 over minus epsilon f is equal to something which is affine in V. Now you just take the primitive of this and you end up with the fact that log of f divided by 1 minus epsilon f is a second order polynomial in V. Or if you prefer, that f is a Fermi Dirac distribution. Okay, so as you can see, and I'm not cheating here, you can really get the fact that f is a Fermi Dirac when the entropy dissipation is equal to 0 in 3 lines. And I think it's really the most, the quickest proof of the H theorem in this context. So at the end, when you put all of this in a slightly more rigorous form, you can end up with the fact that either you have an equilibrium which is a Fermi Dirac, and it is the Fermi Dirac with parameters A and B, which are such that the mass and energy are respectively 1 and 3/2. And when this is not possible, and this happens for very low temperatures, then in fact you end up with a saturated Fermi Dirac statistics, which means that basically f is equal to 1 over epsilon over on a certain ball centered around 0. Okay, in the sequel, I will always let's say, present cases in which you end up with a Fermi Dirac statistics and not with the let's say, a singular case in which you expect a saturated Fermi Dirac statistics. Okay. Now, let me say a few words about the classical entropy method. So this consists in, when you have a strict entropy structure, it consists in looking for a functional inequality which relates the entropy dissipation and the relative entropy, that is the entropy minus the entropy of the equilibrium. And if you have a linear relation between the two, that is, if d of f is bigger than a constant times the relative entropy, then you can replace the minus d of f by minus c0 h of f minus h of f infinity, and you end up with a differential inequality that you can solve thanks to a Schr&ouml type argument. And you end up with the fact that the entropy, the relative entropy, converges exponentially fast to 0. Okay, and the rate that you have in the exponential is exactly the C0 which appears in the functional inequality. Now, when you are in the context of the Boltzmann or Landau equations, or more generally, let's say, collisional kinetic models, all of this is usually called Cherchiniani's conjecture. So we say that the Cherchiniani's conjecture holds whenever you have such a functional inequality between the entropy dissipation that you're looking at and its related entropy. So this is for the vocabulary, let's say. But please remember that when you have the Cherchiniani conjecture, it means that you will automatically get exponentially fast decay towards the equilibrium. And actually, this decay holds for the entropy, but in many cases, the relative entropy controls the square of some norm. And in the case of the classical entropy, this is well known, and this is called the Csiszar-Kullback-Pinsker inequality, which has been obtained many, many years ago by specialists of information theory, basically by founders of information theory. And it tells you that up to a factor 2, the relative entropy is bigger than the square of the L1 norm of f minus f infinity whenever you are looking at positive functions which have integral 1, so basically probability measures. Let's say that at this point that it is a little less known that this inequality also holds in the case of the quantum, let's say Fermi Dirac style entropy. And this is true uniformly in epsilon with the same, basically the same constant. So you have the same inequality, and this can be found, for example, in the paper by Chuguang Lu and Bernd Wennberg, which appeared close to 20 years ago now. So all of this to tell you that when you have the Cherchiniani's conjecture, it not only gives you the exponential decay of the entropy, but the exponential decay in L1 norm also for the solutions of the equation you're looking at. Now, Cherchiniani's conjecture are rather rare, and in the strict sense that I defined here, that is really with a constant and a linear dependence between the entropy and the entropy dissipation. They are basically known in two cases. The first one is the case of the Boltzmann operator with so-called super hard spheres, which means that you put v minus v star to the square in the cross section. You can do some angular dependence also, but I will not be too precise about this. And this was obtained in a classical paper now by Cédric Villani in 2003. And it is quite interesting to see that actually the proof uses deeply the Church-Yannis conjecture for the Landau equation when it is known, and it is known for the Maxwell molecule case, which corresponds to V minus W to the square in the Landau operator. And this was obtained in a paper that I wrote together with Villani now many years ago in '99. So basically we have those two cases in which we have the Church-Yannis conjecture. Let me say one word about the way it is done in the case of the Landau equation. Actually, this is a consequence of two inequalities that you use one after another. The first one is the one which relates the entropy dissipation of Landau with the so-called relative Fisher information, which is this integral of f times gradient f over f plus v to the square. And the second one was known for many years, and actually this is the logarithmic Sobolev inequality of growth, which was, I think, first proven in '75, and which directly tells you that the relative Fisher information is bigger than a constant which is explicit, which has to do with, I don't remember, but it is 2 or 1/2 also, I think. Anyway, this is an explicit constant times the relative entropy. So when you put those two inequalities together, you exactly end up with what you wish, which is the Church-Yannis conjecture for the Landau equation with Maxwell molecules. Okay, so this is for the past in some sense. And now let me say that the group which was formed by Bertrand Lods, Véronique Bagland, and Ricardo Alonso worked a lot on the Landau Fermi Dirac equation in the past years, and so I think it was in the last workshop in which I participated in presence, which was in Granada in maybe 2 years, so it was maybe February of 2020. I had the opportunity to discuss with Bertrand Lods, and he asked me if there was some hope of having a Church-Yannis conjecture style, let's say, result for the Landau Fermi Dirac. And more precisely, he was interested in the case of hard potentials. That is when you put V minus W to the power gamma, with gamma strictly positive in the entropy dissipation. Now, let's say that this is also interesting if you take gamma equal to 0, which would correspond to the classical case in which it was proven in '99 that the Church-Yannis conjecture hold. And I became very interested by his question, and then we worked together with Véronique and Ricardo. And so the question runs like this at the end. Is it possible to show that there is a constant such that when epsilon is, let's say, small enough, there is this direct link between the entropy dissipation of Landau Fermi Dirac and the Fermi Dirac relative entropy, let's say for all reasonable f which are bigger than 0. By reasonable, we mean, for example, that f should be less than epsilon to the -1. And let's say which are normalized. Also, one important point is that in all the theory that they developed, they wanted to have results which are uniform with respect to epsilon when epsilon is small. And so here also, the question is it really possible to get a C, a constant C, which does not depend on epsilon, for epsilon small enough? So, yeah, before explaining what we obtained at the end, let me explain maybe first why I became so much interested in this question. So, for me, it's related to a result that I obtained a few years ago in 2014, in which I showed that for soft potentials, including, let's say, the Coulomb case, there is an inequality between the classical Landau entropy dissipation and the basically a weighted H1 norm to the square of the square root of f. So this is a term which is written on the right-hand side in the inequality. So this is some kind of link between the entropy dissipation and something, but it's more something which is related to smoothness. My feeling is that this inequality is actually quite robust, and I was quite interested in showing that it is indeed very robust, and in order to show that, and of course one has to find slightly different cases from the classical case. And so let me say that this robustness had already been tested in one very interesting paper by Maria Pia Gualdani, François Goltz, Cyril Imbert, and Alexis Vasseur in 2019, in which they basically proved the equivalent of the Caffarelli-Kohn-Nirenberg result for the incompressible Navier-Stokes equation in the case of the spatially homogeneous Landau equation with Coulomb potential. And another result of robustness related to this inequality has been obtained by Bob Strain and Maja Taskovich also in 2019 for the relativistic Landau equation, the special relativistic Landau equation. So we have at least already two directions which show the robustness, and actually this quantum case is a third direction in which this robustness can be shown. So this is for the motivation. Then there are a certain number of reasons to imagine that indeed the Cherchinianis conjecture should hold or could hold for this model. So I selected three of them. The first one is already was known by Ricardo, Ronique, and Bertrand, and this was the fact that exponential convergence towards equilibrium is already known for the Landau Fermi Dirac equation with a rate which is the spectral gap of the linearized operator. And when epsilon go to zero, when the quantum parameter to zero, we know that this lambda epsilon converges to a limit which is the spectral gap of the classical operator. So there is uniformity in epsilon. And this was obtained basically by a spectral analysis of the problem, and which uses also the techniques by Maria Pia Gualdani, Clément Mou, and Stéphane Michler. So when you have let's say an exponential convergence to equilibrium, you can hope for Cherchinianis conjecture, though there is no equivalence between the two, and let's say the Cherchiniani conjecture in general is rather more difficult to get than the exponential convergence toward equilibrium. But nevertheless, it's a clue that this could hold. The second reason why we can hope for that is that there has been a treatment of the classical Landau equation with Coulomb potential, which makes use of the kind of entropy inequalities that look like the Cherchinianis conjecture, but it is in a case of soft potentials, and so it cannot be the full Cherchinianis conjecture, because we are in a situation in which it's not possible to get exponential convergence. And I mean, this was really detailed in the talk by Renjun yesterday, so I will not insist on that too much. But we obtained a result together with Ling Bing He and Kleber Carapat also a few years ago about this. And this is done using entropy inequalities. So we know that entropy inequalities can be used also for large time behavior in the context of the Landau equation. And the final result is that we also have a result for hard potentials. And so this is part of a general study of, let's say, close to optimal inequalities related to the paper that I wrote in 2014. And let's say this appears also in the works that was done together with José Antonio Carrillo, Matías Delgadino, and Jeremy Wu on the let's say gradient flow structure of the Landau equation. So here it is in the case of the hard potential, and let's say in the context of the smoothness estimates, it's really possible to do something in the case of hard potentials, and it's possible to get an estimate which is close to optimal, in the sense that, as you can see on the slide, you have the Landau, the classical Landau entropy dissipation that you can bound between from above and from below by a quantity which is identical and which is very close to the quantities that you find when you're trying to do let's say a precise spectral analysis of the linearized kernel. That is, you have this cross product between V and gradient f over f, for example, which appear. So they are very, very close, except that you have this C minus of f and C plus of f, which depends on one side on some LP norm of f and on the other side of some moment of f. Anyway, I don't want to comment too much about this slide. Let's just say that something was already known for hard potentials. So as you can see, there are many reasons to think that the Ciarcignani conjecture may hold in this context. So let me state the main result that we obtained together with Ricardo, Véronique, and Bertrand. So the point is the following. There is a link, there is a sort of a linear link between the entropy dissipation of the Landau Fermi Dirac operator and the relative entropy, and the constant that you have is something which I call lambda, and which depends on, let's say, at moments of f and LP norms of f. And also you have a term which is 2a epsilon minus epsilon squared times something, where a epsilon is the parameter which appears in the Fermi Dirac equilibrium, so parameter related to the temperature, and it is something which tends to a finite limit when epsilon go to 0. So this limit is either 1 or 1/2, I don't remember, but anyway, there is a limit when epsilon go to 0. And so, as you can see, the second term is minus something times epsilon square. And so when epsilon is small enough, this will be strictly positive, okay? Let me add that this holds provided that f is not too close to 1 over epsilon. So this is a sense of the hypothesis, which is on the first line of the computations, that the infimum of 1 minus epsilon f should be bigger than a constant. And all the things which appear in this inequality, that is a moment, the LP norm, this constant K0, all of this is known thanks to the works by Alonso, Bagland, and Lods, to be propagated uniformly in time up to infinity by the Landau Fermi Dirac equation. So this, in fact, has as a consequence, once again, the exponential convergence towards equilibrium for the solution of this equation. So this is what I say in this slide. And all of this holds uniformly in epsilon when epsilon is small enough. Let's say that with respect to the proof that they already had, the one that we have now is much shorter. All constants can be explicitly computed, so there are no compactness arguments, whereas there was one in their original proof. So that is the positive aspects, let's say. And now there are also negative aspects. As always, with those methods, the rate which is obtained is not as precise as when you do spectral theory. So you do not necessarily get a rate which is a spectral gap at the end. and the interval on which of epsilon on which it holds is probably smaller than the one in the proof that they had. So there are good points and bad points, let's say, when you use this method of the Churchinianist conjecture. Okay, I think that I have only 2-3 minutes for the proof, so I will not detail things really seriously. Let me just say that if you have understood the proof of the case of equality in the H theorem for the Landau Fermi Dirac, then you have all the ingredients which are needed to do the proof here. And basically, the idea is that you pick once again this cross product between V minus W and the gradient of F at point V and gradient of F at point W. But instead of saying that this is 0, you say that this is something, and you call this something Q, okay? And you do all the steps that you already did. So you expand, you multiply by Wi F of W, you integrate, you write everything in the, let's say, simplest possible way. And what you end up with at the end, so I will not detail this, is that the entropy dissipation of Landau Fermi Dirac dominates a quantity, which is the one which is in the first line of the slide, which is very close to the, let's say, quantum Fisher information, or let's say Pauli exclusion principle like relative Fisher information for F. The bad point is that the constant K which is inside is not the one that you would like to have. And actually, you have to use then the kind of logarithmic Sobolev inequality that you can find, for example, in a paper by José Antonio, Philippe Laurenceau, and Rezo Rosado, that is that holds when in front of V you have 2A, where A is the parameter which appears in the Fermi Dirac. So you have K and you should have 2A to simplify. And so in order to do the final estimate, you have to take the one that you have in which you have K, you have to put 2A by force inside, and you have to remove the difference between this K and this 2A. And when you do that, you see that at the end, you end up with the fact that the entropy dissipation is bigger than 2A times the entropy, the relative entropy, minus a term, which is a difference between this K and this 2A to the square. And it happens that when you write precisely what are K and 2A, you see that this is a difference of some quantity related to F and to the equilibrium. And so you do some further analysis, and you end up with the fact that you can bound those things by some L1 norm, which itself can be bound by the entropy, the relative entropy, thanks to the modification of the Chisard-Kullback inequality that appeared in the paper by Xu-Kwang and Bernd. When you do all of this, you end up with the main statement. So I will, sorry, I think I went backward. So let me finish by saying a few words about of comments and maybe perspectives about all of this. So the first thing is that this was the occasion for me to, in some sense, to read again seriously the very old paper that I wrote together with Villani in '99, and to try to make it as simple as possible. And now I have some hope that we can even remove the use of the entropy itself in the paper, and maybe end up with something in which we obtain, let's say, inequalities in which we don't have to suppose that F as a finite entropy. So So that's the first thing. And also probably the small epsilon hypothesis in the LFD equation is not really necessary. So first link, first line of work, I mean, would be to sort of clean a little all of this and remove things which are not really necessary. Maybe a more important thing would be to try to go to Coulomb potentials. So in that case, the Chartinianist conjecture cannot be true, but you can replace it maybe by a conjecture in which you have weights. And so we know that this is exactly what happens in when you look at spectral gaps, and it's what we saw in the talk by Renjun. We were also able to do that together with Ricardo, Veronique, and Bertrand in the case of moderately soft potentials, but we have not yet been able to go to Coulomb potentials, which are much more difficult. Then it would be interesting probably to try to look at the case of Bose-Einstein. In that case, necessarily things has to be changed a lot. There is a possibility of appearance of a condensate, so one has to think much more probably to what can be done. But I think it's interesting maybe to try to do something. And finally, and maybe for me most importantly, my feeling is that there is maybe something which can be done now on Boltzmann-like or weak turbulence-like equations in which there is, let's say, terms which are not quadratic. So either, let's say, Boltzmann-Nordheim or some of the weak turbulence equations, and maybe get some kind of Chartinianist conjecture in this situation. This is probably the most speculative part, but maybe also the most interesting one. Okay, I think I will stop now.
Thank you, Laurent, for the nice talk. So please, is there any question? Just, yeah, Robert, I can see that. Yeah, go ahead, Robert.
Oh, hi, Laurent. I have a question. What is the situation? Is the existence for Landau Fermi Dirac with it hard potentials similar to Landau without the Fermi Dirac for hard potentials, or is it?
Actually, there is one more difficulty. In some sense, it's much easier if you do it for a given epsilon. So if you do it for a given epsilon, it's very easy. The point of the theory by Ricardo, Veronique, and Bertrand is that they wanted to have something which is uniform in epsilon, and so in some sense which would give you also the result in the case of the traditional Landau. So they sort of wrote down a very complete theory in the case of hard potentials. And one of the difficulties is that instead of having f everywhere, you have like f minus epsilon f square. And in many cases, you cannot exploit the minus. So of course, when you can exploit the minus, it helps you. But in many cases, it's not possible. And for example, if you want to get moments, it becomes a mess. And they have a very complete theory of that. That together with them, actually, we sort of extended in the case of moderately soft potentials more recently.
So can you think of Landau Fermi Dirac as some kind of a parabolic system then still, or is it?
Oh yeah, I think so. Yeah.
So can you? This is my actual real final question: is can you? Does it make sense to try to apply sort of the result that you discussed to get the decay for large data, and then maybe also to get the to have an analog of the result that you proved, I think, in 2020 with Lingming He and Jiang for Landau with a monotonicity type formula?
Yeah, so the point is we don't yet have anything in the Coulomb case. So up to now, it's okay up to gamma equal to -2. And so the first step would be, I think, to get something in the Coulomb case. And then, of course, we can hope that it's still possible to do what we did with Jingcheng and Lingbing, but it's still quite speculative, and already the moderately soft case is very, very technical. So hopefully.
Thank you.
Is there any other question, please? Yeah, please, Rico. Yeah.
First of all, thanks for the very nice talk. I have a more general question. So you mentioned cases where the Ciaccignani's conjecture is true, and then you said at the very end that for Coulomb, for the Coulomb case in the Landau equation, this is not the case. So can you say a little bit more about, let's say, counter examples, or where you know it's not true, or you have to use a different form of the inequality?
Yeah, sure. So there are direct counterexamples, I think, in a paper by Bobilev and Ciaccignani himself, which date back to the 80s, for the Boltzmann equation with, let's say, standard potentials. So let's say hard potential, hard spheres, soft potentials. For all of these, they have counterexamples, and I'm not sure that this was written in the case of the Landau equation, but my feeling is that you can probably write the same kind of counterexamples in that case. Anyway, in the case of the Landau with Coulomb, we don't even expect it to hold. So in some sense, we know that thanks to the spectral analysis, we know that there is really no hope of getting Ciaccignani's conjecture. So the whole point is to replace it by something which has some, but we can hope exists. And let's say typically what we can hope to get is an inequality in which you have some weight, which looks like the weight that you get in spectral gap-like inequalities, let's say.
Okay, thank you.
Is there any other question?
Hi, sorry.
Go ahead, Jeremy.
Laurent, thank you for the very nice talk. I have two questions. One is somewhat general, the other is kind of specific. I'll start with the general one. You said that you can think of the entropy dissipation for the Fermi Dirac for Landau as also coming from the grazing collision from that of Boltzmann. Does that, is there a proof of that, or do you expect that you can say solutions for the Boltzmann Fermi Dirac converge in the grazing collision limit to solutions of the Landau Fermi Dirac independent of this epsilon?
Yeah, so you actually you asked two different questions.
Sorry.
The one is much easier than the other one.
Okay.
So the first one, which is the link between the entropy dissipations of, let's say, Boltzmann-Nordheim and Landau Fermi Dirac, this corresponds to selecting one given f. Okay.
Yes.
And then trying to do the limit. Mm-hmm. So this can be done, let's say, formally very easily. And as a consequence, my feeling is that if you select an f which is smooth enough, which has a good decay and which is bounded below by a nice thing, then I'm almost completely sure that you will get a theorem out of this. Mm-hmm. The second question is quite different. It really, you look at the solutions. And there I must say that I have no good intuition about this, in the sense that I never worked directly myself on Boltzmann-Nordheim. And so I'm not familiar enough with what is known and what is not known to know if you can pass to the Landau Fermi Dirac out of it. And even more, if you want it to be epsilon independent, this I cannot really answer.
Okay. But for fixed epsilon, you could use sort of the same formal computations that you wrote, and as well with Degond and wrote. Like you could
I would be for a given epsilon, I would be definitely more optimistic.
Okay, thank you. I don't want to hold up the time, so I'll probably send you an email about the more specific question. Thank
With
you.
pleasure.
Okay, so thank you, Jeremy. So yeah, I propose to move on.